The blade and fluid velocities for an axial turbine are shown in the figure. The magnitude of absolute velocity at entry is 300 meter per second at an angle of 65 degree to the axial direction, while the magnitude of absolute velocity at the exit is 150 meter per second. The exit velocity vector has a component in the downward direction, given that the axial or horizontal velocity is the same at entry and exit. The specific work is, so for this configuration, according to this diagram, we need to find the specific work of the axial turbine. Now to calculate the specific work, let's make the velocity triangle at the entry and at the exit of the turbine blade. Now let V1 be the absolute velocity at the entry, which is given as 300 meter per second, which enters the blade at an angle of 65 degree. So if we calculate the horizontal and vertical component of this velocity, so the horizontal component of this velocity will be V1 cos 65 degree and the vertical component is V1 sin 65 degree. Similarly, at the exit, V2 is given in the problem, which is 150 meter per second. Suppose it exit at the angle beta, and beta is not given in the problem. So the horizontal component at the exit will be V2 cos beta and the vertical component is V2 sin beta. Now the information provided in the problem is that the horizontal component at the entry as well as at the exit are equal. So we can write V1 cos 65 degree is equal to V2 cos beta. So from here, cos beta will be equal to V1 by V2 cos 65 degree. Now in the problem, V1 is 300 meter per second and V2 is 150 meter per second multiplied by cos 65 degree. So this value will be 0.84523. So from here we can calculate beta, which is equal to cos inverse of this. Therefore beta will be equal to 32.303 degrees. So the specific work, which is the work per unit mass, is given by V1 sin alpha minus V2 sin beta multiplied by the blade velocity u, which is 150 meter per second in the problem. So let's say this be small w. So specific work will be equal to V1 sin alpha, that is 300 into sin 65 degrees minus V2 sin beta. So V2 is in the opposite direction. So let's write minus 150 for V2 sin beta, and beta is 32.303 degree whole multiplied by the blade velocity, which is 150 meter per second in this problem. Now from here, if we calculate, we get specific work will be 52,807.77 joule per kilogram. So if we calculate this value kilojoule per kilogram, we get specific work will be 52.8 kilojoule per kilogram approximately. Okay, so the correct answer here is 52.8 kilojoule per kilogram. For detailed information, you can refer to the NPTEL course. Lecture number 21, the work done, degree of reaction, losses and efficiency on turbomachinery's aerodynamics by Professor Bhaskar Roy and Professor A.M. Pradeep of the Department of Aerospace Engineering at IIT Bombay.